Hi everyone, my name is Hannah Levier, and I'm the project manager for Team Aurora. We are working on the dual-use wideband microphone array system. Our system is needed because as issues in equipment and air leaks have been found on the space stations, manual time and labor has gone into finding the source of air loss with handheld detectors by astronauts. Our project aims to reduce the time and labor to find the issues by detecting ultrasonic anomalies that can't be heard by the human ear, and then alert the crew of the issue with the intensity of the leak. The dual-use design of our project will increase the efficiency of the system and create a more desirable design for deep space mission applications. The system is designed to be dual-use to consider weight and power constraints. The system will simultaneously detect both voice and ultrasonic frequencies so that the two functionalities don't have to be designed and built separately, which would require a larger amount of materials and consume more power.
Hello everyone, I am Billy Flores and this is a top-level diagram of our project. The system is accepting two frequency bands, ultrasonic and human speech, which will travel through the dotted and dashed line path, respectively. The two frequency bands will be channeled to their own filtering and amplification subsystems. A physical toggle switch will allow the user to enable or disable communication when desired. When the system detects an ultrasonic frequency or leak, an audible and visual warning will be outputted.
My name is Daniel Lewis, and I'm responsible for the microphone array subsystem and the voice filtering and amplification subsystem. The array is made up of micro-electromechanical, or MEMS, microphones. MEMS microphones are lightweight and low power, which make them ideal candidates for space missions. MEMS microphones are very small and require PCB mounting, so to keep our design modular and flexible, we are using evaluation boards. The subsystem diagram has blue blocks for elements in the subsystem and interacts with the white blocks with elements from other subsystems. We are using two types of MEMS microphones, the first for voice with noise canceling capabilities, and the second for ultrasonic detection with a frequency range up to 80 kilohertz. The ultrasonic MEMS microphones will be expanded up to 8 channels for the stretch goal of sound localization, as denoted by the /8 on the signal line in the diagram. A 3.3 volt DC power source is used for both types of microphones. The voice filtering channel receives a positive and negative differential output from the noise canceling microphone in the range of 25 Hz to 20 kHz. These signals are run through the difference amplifier at unity gain. A double pole, double throw communication toggle switch passes the audio signal to the filter, as well as sends a hot mic voltage signal to the display system. A 200 Hz to 6 kHz second order Chebyshev passive bandpass filter is used to attenuate the signal to the required bandwidth for voice communication. Additional filtering could be required and would be cascaded into our system before the signal is passed to the audio output system.
Hello, my name is Jesus Hernandez, and I'm responsible for the ultrasonic filtering amplification subsystem. The input signals on the left coming from the MEMS array vary from 100 Hz to 80 kHz, this being the frequency constraints of the MEMS microphones. The input voltages are to be determined once we begin testing our subsystems. Because of this, the exact gain of the amplifier has yet to be determined. The amplifier used is a TLE 2141 ACD as an inverting operational amplifier. It was chosen for its high slew rate, high power bandwidth, and low distortion characteristics. The anticipated output voltages range from 0 to 10.6 volts peak to peak for rectification. The amplified signal is output to a 6th order Chebyshev passive high pass filter with a 20 kHz cutoff frequency. All frequencies above 20 kHz will have additional noise filtering, which will be determined upon testing and output to the ultrasonic rectification stage.
We're now at the ultrasonic rectification subsystem. It will receive an amplified and filtered ultrasonic signal with a voltage range from 0 to 10.6 volts peak to peak. The signal will pass through a half-wave rectifier that is designed using a Schottky diode and will output a voltage varying from 0 to 5 volts DC to the warning microcontroller. The rectified output signal is not meant for transistor or transistor logic, but to gauge the intensity of the ultrasonic source through voltage representation.
Hello everyone, my name is Micah Snell and I'm responsible for the warning subsystem. My subsystem consists of an Arduino Mega, 3 different colored LEDs, and a push button. The microcontroller will sample the output of the ultrasonic rectifiers and determine if an ultrasonic signal is present. When an ultrasonic signal is positively identified, the microcontroller will output an auditory and visual warning, as well as send a notification to the display subsystem. The auditory warning will be a 5 volts peak-to-peak PWM signal with a frequency of 1 kilohertz, and the rate at which the signal occurs will increase from once per second to 4 times per second based on the intensity of the detected leak. The visual warning will be conveyed by activating one of the 3 LEDs, and as with the auditory warning, the LED that is activated will depend on the intensity of the signal. The user will be able to silence the auditory warning by pressing the push button for less than 3 seconds, and can reset the warning system by pressing for more than 3 seconds.
Hello everyone, my name is Anthony Woods and I'm responsible for the visual output system. Within my subsystem, each component receives a 5-volt DC signal via 2 individual external power sources. This subsystem will be receiving data from the warning microcontroller via a USB connection into the Raspberry Pi. This information will represent the intensity of the ultrasonic signal. The serial data is sent from the Raspberry Pi into the LCD screen via an HDMI connection to display the pertinent data information related to the intensity of the signals, the system status, the state of the communication toggle switch, and a 1D sound localization feature. We will be utilizing the Raspberry Pi 4 Model B microcomputer to accept all data that is received from the warning microcontroller. The software will operate using the Pi on the Arduino IDE, which also allows for a cross-platform experience in Windows, Mac OS, and Linux environments.
Next, we will be discussing the audio output subsystem. The audio output subsystem receives the warning signal and voice communication simultaneously, mixes these signals, and outputs the audible sound to a speaker for crew communications and alerts. When a leak is detected, the warning microcontroller will send the warning signal to the mixer. Before being mixed, the input signal amplitude is reduced to a 3.2 volt peak-to-peak using a voltage divider. The filtered voice signal coming into the mixer is a 2.4 volt peak-to-peak ranging from 200 to 6 kilohertz. The voice input is connected to a potentiometer to increase and decrease the volume so that communications is not louder than the warning sonification. Using a TLE 2141 ACD summing op amp, the 2 input signals are mixed and output to an off-the-shelf power speaker for volume adjustments.
The power supply subsystem is going to use one main AC to DC converter with a voltage bus to increase the efficiency of the system. The voltage bus will be designed to supply each subsystem of the project with its necessary voltage.
We are now moving away from system design and into system testing. This is the ultrasonic generator subsystem. It is made up of 2 independent units. The leak simulator at the top will be constructed from PVC and will have a pressure gauge to measure the enclosure pressure. The air compressor will be attached to the system while charging. The second gauge is for the pressure regulator, which will allow the user to set the leak intensity by turning the regulator knob. The leak simulator is designed to simulate real-life ultrasonic anomalies. The frequency generator at the bottom is comprised of a signal generator and a piezo speaker. The signal generator will drive the speaker at specific frequencies from 20 kilohertz to 60 kilohertz. Both systems are meant to test the ultrasonic detection function of our system.
Several of the challenges we are tracking with our system include the difficulty of working with ultrasonic frequencies. Also, we're closely monitoring the impact that COVID-19 may have on our project's overall timeline.
This proof of concept's primary focus has revolved around the theme of modularity. The design process we have followed when constructing the amplification, filtering, and rectification stages, paired with the ability to create multiple MEMS arrays, allows for the expansion of each subsystem in a modular fashion. Ultimately, this system could be used in many other real-world scenarios to monitor and detect industry-specific anomalies.
The table seen here describes the major milestones for the success of our project. Team members have already begun construction of their subsystem and have agreed to conduct full system implementation and testing over the winter break for us to successfully have our project ready for TSGC NASA Spring Showcase.
Thank you to NASA TSGC for sponsoring and funding our design challenge. Also, thank you to our sponsor, Mr. George Salazar, Principal Investigator Dr. Richard Campo, and Texas State faculty for helping us with our design-specific questions.